All right. So last time we talked a little bit about a more general understanding of the meaning of kcat, this really important steady state catalytic parameter in thinking about enzymes. So now let's take a similar approach to thinking about Km. Now, as a quick reminder, if you remember, for the basic Michaelis-Menten equation, if, as you recall, we can assume or we know that the Michaelis complex is in thermodynamic equilibrium with the free enzyme and the substrate, that under those circumstances, Km essentially equals the dissociation constant of the substrate from the enzyme if, right, ES is in thermodynamic equilibrium, right? With free enzyme and substrate, right? So under those circumstances, it's fairly easy to understand what Km means, right? But when the mechanisms get more complex, as we saw last time, in thinking about like the chymotrypsin, chymotrypsin, the serine protease mechanism, right? Then Km becomes a little more complex. Under these circumstances, for a mechanism like the trypsin and chymotrypsin mechanism, Km, and for many more, or all more complex enzymes, becomes a function of all of the underlying equilibrium constants and or first order rate constants that describe the process, right? So under those circumstances, Km is a little less intuitive to understand in the way we want to think about it, or the way you can think about it in the case of the simple Michaelis-Menten mechanism as a dissociation constant. But even we saw under lots of circumstances for simple enzymes like this one, where we cannot assume thermodynamic equilibrium. We cannot correctly think of the relationship between the Michaelis complex and the free enzyme as being in thermodynamic equilibrium. We have to think about Km again as the combination of these underlying rate constants, right? In this case, of course, K minus 1 plus K2 over K1, right? So an important additional way to think about this, right? And one of the reasons, so I sort of point out this idea about why you have to be careful thinking about Km, the simple-minded way to think about it as a binding constant for the enzyme to the substrate can get you into trouble, is because if you think about an enzyme that has that is correctly described by the Briggs-Haldane mechanism, the steady state mechanism, as I've written it here, there are two ways to get a high Km. And again, you want to think about Km as a dissociation constant. The bigger that number, right, the larger Km here happens to be, the weaker you would think the binding was, right? So as that goes up, right, you think, okay, the binding is weaker. But if you're dealing with an enzyme that does not adhere to the simple Michaelis-Menten assumption of thermodynamic equilibrium here, there are two ways to get Km to be big. Km could be big either because K minus 1 is large, right? Which would be, you know, that would fall into the category you think of as the system approaching thermodynamic equilibrium. And so if K minus 1 is large, binding is weak, that's good. But there's another way to get Km intrinsically to be big. Remember, there's another term in this numerator. What happens if the rate constant for a Briggs-Haldane mechanism is big? What if K2, right, our rate constant for doing chemistry, is a lot larger than K minus 1? Everything else being equal, Km is going to be big. But you've learned nothing about, or you know nothing from that parameter about the dissociation constant or the strength of the interaction between the enzyme and the substrate, right? So this is why you've got to be really careful in interpreting the Km as being a measurement of the dissociation constant for the substrate with the free enzyme, unless you know that a simple Michaelis-Menten thermodynamic pre-equilibrium, unless you know that applies, you got to be careful. All right. Even so, having said all of that, there is still a fairly simple, fairly straightforward way to think about Km under essentially all circumstances, right? Even for these more complex reaction schemes. And it has to do with something we talked about before when we thought about how these enzyme substrate reactions behave experimentally, right? If you think about that initial rate behavior for an enzyme under steady state conditions, right? Remember, we map that initial rate out, we get this saturation kinetics, a function of substrate concentration. And remember, up here, right, at the asymptote is, of course, our Vmax, right? And remember what happens right here at 1/2 Vmax, right? The concentration of substrate at which we achieve 1/2 Vmax, that is the Km, right? Remember? Okay, that's going to be true even for the Briggs-Haldane mechanism, even for the serine protease mechanism, this multi-step mechanism we talked about before, where Km is this more complex function, under in even more complex mechanisms under steady state conditions, measuring the initial rate, 1/2 Vmax is still going to give you the Km, which means a relatively simple and always correct way to think about Km is that the Km is the concentration of substrate, right, that's needed to achieve effective catalysis, right? Right? So that gives you an operational measurement. If you're reaching about 1/2 of the maximum rate the enzyme can go, the amount of substrate you need to get there tells you something, right, about how much or how well this enzyme is working under a given set of circumstances for a given amount of substrate. Because that half saturation point tells you how much substrate you need to get that reaction to produce product at some reasonable rate. So thinking about Km with this sort of mindset, the amount of substrate I need to get sort of the enzyme going at about half its maximum rate isn't always a correct way to think about it, even if the underlying mechanism is more complex than the simple Michaelis-Menten mechanism. Okay, now there's one other way to think about Km, another sort of definitional way to think about Km. If this is sort of the one way, there's another way to think about it that becomes important for something later, right? And that you can think about Km as an effective dissociation constant, even for these more complex mechanisms, if you consider it to be the equilibrium constant between free enzyme and substrate and all bound forms of the enzyme. So that would include the enzyme substrate complex, the enzyme product complex, and any other bound forms of the enzyme, right? Now, you can think about it under these circumstances as kind of an average macroscopic KD between free enzyme and any potentially bound species of the enzyme. This idea, this basic concept is theoretically consistent with this idea of thinking of the Km as being this sort of half saturation idea, right? And it's also a cautious interpretation of Km as being kind of like a KD. And one of the main reasons for thinking about Km this way has to do with the next kinetic parameter we need to discuss, which is super important in thinking about enzymes, and that is the ratio of Kcat to Km.